Hello everybody and welcome back to day 53 of 100 Days of Code with me, Lilly Code. So we're going to continue on watching Nana's Kubernetes tutorial. You can see it down here. Kubernetes tutorial for beginners. So we've been watching this for the last few days. 4 hours. It's taken me a good few days now. So we're still going. But that's fine. You know, we're working our way through it. And just to mention as well, yesterday on Twitter, I got this message a few days ago actually saying, "You'll have to excuse my ignorance. This is the only Nana I know." So it's from a cartoon called Nana. Is it a cartoon? Slice of Life Sojo. The two protagonists share the same name, and it has an anime adaptation. So I was talking away to my friend here, and I said, "Oh, brilliant! I'll have to watch it, Sir Loop, and I'll wear my Full Metal Alchemist t-shirt just for you." So I have my Full Metal Alchemist t-shirt on here. We can see Alphonzo in the picture. Oh, go on, Alphonzo, the brother from Full Metal Alchemist, the metal brother. I recommend everybody watch Full Metal Alchemist. It is like the best anime series ever. It's so heartwarming, touching, the story sad, just absolutely fabulous. So check out Full Metal Alchemist. Check it, Alphonzo. That's Alphonzo. That's the expression that he makes. And on that, anyway, we will continue into the video. I also got a load of comments that I hadn't seen on my video. So look, guys, thanks so much for interacting. Like, it's just wonderful to get the few words of encouragement from you guys. I really appreciate it. And if you are enjoying it, like, please do like and subscribe. But that's up to you. I'm just buzzing here anyway, and I appreciate every single one of you interacting in any way with any of my content. It's brilliant. But it helps it get out there if, you know, people subscribe and they like it and stuff. So as you wish, and just have a lovely day, and let's get going on the video. So thanks. Okay, let's go. Me and Alfonso are ready.
Kubernetes cluster, you would need a couple of Kubernetes components. So you would need a stateful set, which is for stateful applications like databases. You would need a config map with external configuration. You would need a secret where some credentials and secret data are stored. You would need to create the Kubernetes user with its respective permissions, and also create a couple of services. Now, if you were to create all of these files manually by searching for each one of them separately on internet, it would be a tedious job. And until you have all these YAML files collected and tested and tried out, it might take some time. And since Elastic Stack deployment is pretty much the standard across all clusters, other people will probably have to go through the same. So it made perfect sense that someone created these YAML files once and packaged them up and made it available somewhere so that other people who also use the same kind of deployment could use them in their Kubernetes cluster. And that bundle of YAML files is called Helm chart. So using Helm, you can create your own Helm charts or bundles of those YAML files and push them to some Helm repository to make it available for others, or you can consume, so you can download and use existing Helm charts that other people pushed and made available in different repositories. So commonly used deployments like database applications, Elasticsearch, MongoDB, MySQL, or monitoring applications like Prometheus that all have this kind of complex setup, all have charts available in some Helm repository. So using a simple Helm install chart name command, you can reuse the configuration that someone else has already made without additional effort. And sometimes that someone is even the company that created the application. And this functionality of sharing charts that became pretty widely used actually was one of the contributors to why Helm became so popular compared to its alternative tools. So now if you have a cluster and you need some kind of deployment that you think should be available out there, you can actually look it up either using command line. So you can do Helm search with a keyword, or you can go to either Helm's own public repository, Helm Hub, or on Helm charts pages or other repositories that are available. And I will put all the relevant links for this video in the description so you can check them out. Now, apart from those public registries for Helm charts, there are also private registries, because when companies started creating those charts, they also started distributing them among or internally in the organization. So it made perfect sense to create registries to share those charts within the organization and not publicly. So there are a couple of tools out there that are used as Helm chart private repositories as well. Another functionality of Helm is that it's a templating engine. So what does that actually mean? Imagine you have an application that is made up of multiple microservices, and you're deploying all of them in your Kubernetes cluster. And deployment and service of each of those microservices are pretty much the same, with the only difference that the application name and version are different, or the Docker image name and version tags are different. So without Helm, you would write separate YAML files, configuration files for each of those microservices. So you would have multiple deployment service files where each one has its own application name and version defined. But since the only difference between those YAML files are just a couple of lines or a couple of values, using Helm, what you can do is that you can define a common blueprint for all the microservices, and the values that are dynamic or the values that are going to change replace by placeholders. And that would be a template file. So the template file would look something like this. You would have a template file which is standard YAML, but instead of values, in some places you would have the syntax, which means that you are taking a value from external configuration. And that external configuration, if you see the syntax here, .values, that external configuration comes from an additional YAML file, which is called values.yaml. And here you can define all those values that you're going to use in that template file. So for example, here, those 4 values are defined in a values YAML file. And what .values is, it's an object that is being created based on the values that are supplied via values YAML file and also through a command line using --set flag. So whichever way you define those additional values, they're combined and put together in .values object that you can then use in those template files to get the values out. So now instead of having YAML files for each microservice, you just have one, and you can simply replace those values dynamically. And this is especially practical when you're using continuous delivery, continuous integration for your application, because what you can do is that in your build pipeline, you can use those template YAML files and replace the values on the fly before deploying them. Another use case where you can use the Helm features of package manager and templating engine is when you deploy the same set of applications across different Kubernetes clusters. So consider a use case where you have your microservice application that you want to deploy on development, staging, and production clusters. So instead of deploying the individual YAML files separately in each cluster, you can package them up to make your own application chart that will have all the necessary YAML files that that particular deployment needs, and then you can use them to redeploy the same application in different Kubernetes cluster environments using one command, which can also make the whole deployment process easier. So now that you know what Helm charts are used for, let's actually look at an example Helm chart structure to have a better understanding. So typically, chart is made up of such a directory structure. So it would have the top level would be the name of the chart, and inside the directory you would have following. So chart.yaml is basically a file that contains all the meta information about the chart. Could be name and version, maybe list of dependencies, etc. Values.yaml that I mentioned before is a place where all the values are configured for the template files. And this will actually be the default values that you can override later. The charts directory will have chart dependencies inside, meaning that if this chart depends on other charts, then those chart dependencies will be stored here. And templates folder is basically where the template files are stored. So when you execute Helm install command to actually deploy those YAML files into Kubernetes, the template files from here will be filled with the values from values.yaml, producing valid Kubernetes manifest that can then be deployed into Kubernetes. And optionally, you can have some other files in this folder, like a README or license file, etc. So to have a better understanding of how values are injected into Helm templates, consider that in values.yaml, which is a default value configuration, you have following 3 values: image name, port, and version. And as I mentioned, the default values that are defined here can be overridden in a couple of different ways. One way is that when executing Helm install command, you can provide an alternative values YAML file using values flag. So for example, if values YAML file will have following 3 values, which are image name, port, and version, you can define your own values YAML file called myvalues.yaml, and you can override one of those values, or you can even add some new attributes there. And those two will be merged, which will result into a .values object that will look like this. So it would have image name and port from values.yaml and the one that you overrode with your own values file. Alternatively, you can also provide additional individual values using set flag, where you can define the values directly on the command line. But of course, it's more organized and better manageable to have files where you store all those values instead of just providing them on the command line. Another feature of Helm is release management, which is provided based on its setup. But it's important to note here the difference between Helm versions 2 and 3. In version 2 of Helm, the Helm installation comes in two parts. You have Helm client and the server. And the server part is called tiller. So whenever you deploy Helm chart using Helm install my chart, Helm client will send the YAML files to tiller that actually runs or has to run in a Kubernetes cluster. And tiller then will execute this request and create components from these YAML files inside the Kubernetes cluster. And exactly this architecture offers additional valuable feature of Helm, which is release management. So the way Helm client server setup works is that whenever you create or change deployment, tiller will store a copy of each configuration client sent for future reference, thus creating a history of chart executions. So when you execute Helm, upgrade the chart name, the changes will be applied to the existing deployment instead of removing it and creating a new one. And also, in case the upgrade goes wrong, for example, some YAML files were false or some configuration was wrong, you can roll back that upgrade using Helm rollback chart name command. And all of this is possible because of that chart execution history that tiller keeps whenever you send those requests from Helm client to tiller. However, this setup has a big caveat, which is that tiller has too much power inside the Kubernetes cluster. It can create, update, delete components, and it has too much permissions. And this makes it actually a big security issue. And this was one of the reasons why in Helm 3 they actually removed the tiller part, and it's just a simple Helm binary now. And it's important to mention here because a lot of people have heard of tiller, and when you deploy a Helm version 3, you shouldn't be confused that tiller isn't actually there anymore. In this video, I will show you how you can persist data in Kubernetes using volumes. We will cover three components of Kubernetes storage: persistent volume claim, and storage class, and see what each component does and how it's created and used for data persistence. Consider a case where you have a MySQL database pod which your application uses. Data gets added, updated in the database. Maybe you create a new database with a new user, etc. By default, when you restart the pod, all those changes will be gone because Kubernetes doesn't give you data persistence out of the box. That's something that you have to explicitly configure for each application that needs saving data between pod restarts. So basically you need a storage that doesn't depend on the pod lifecycle, so it will still be there when pod dies and new one gets created. So the new pod can pick up where the previous one left off. So it will read the existing data from that storage to get up-to-date data. However, you don't know on which node the new pod restarts, so your storage must also be available on all nodes, not just one specific one, so that when the new pod tries to read the existing data, the up-to-date data is there on any node in the cluster. And also, you need a highly available storage that will survive even if the whole cluster crashed. So these are the criteria or the requirements that your storage, for example, your database storage, will need to have to be reliable. Another use case for persistent storage, which is not for database, is a directory. Maybe you have an application that writes and reads files from pre-configured directory. This could be session files for application or configuration files, etc. And you can configure any of this type of storage using Kubernetes component called persistent volume. Think of a persistent volume as a cluster resource, just like RAM or CPU, that is used to store data. Persistent volume, just like any other component, gets created using Kubernetes YAML file, where you can specify the kind, which is persistent volume, and in the specification section, you have to define different parameters, like how much storage should be created for the volume. But since persistent volume is just an abstract component, it must take the storage from the actual physical storage, right? Like local hard drive from the cluster nodes, or your external NFS servers outside of the cluster, or maybe cloud storage like AWS, block storage, or from Google Cloud Storage, etc. So the question is, where does this storage backend come from? Local or remote or on cloud? Who configures it? Who makes it available to the cluster? And that's the tricky part of data persistence in Kubernetes, because Kubernetes doesn't care about your actual storage. It gives you persistent volume component as an interface to the actual storage that you as a maintainer or administrator have to take care of. So you have to decide what type of storage your cluster services or applications would need and create and manage them by yourself. Managing meaning do backups and make sure they don't get corrupt, etc. So think of storage in Kubernetes as an external plugin to your cluster. Whether it's a local storage on actual nodes where the cluster is running or a remote storage, doesn't matter, they're all plugins to the cluster. And you can have multiple storages configured for your cluster where one application in your cluster uses the local disk storage, another one uses the NFS server, and another one uses some cloud storage. Or one application may also use multiple of those storage types. And by creating persistent volumes, you can use these actual physical storages. So in the persistent volume specification section, you can define which storage backend you want to use to create that storage abstraction or storage resource for your applications. So this is an example where we use NFS storage backend. So basically we define how much storage we need, some additional parameters to that storage, like should it be read-write or read-only, etc., and the storage backend with its parameters. And this is another example where we use Google Cloud as a storage backend, again with the storage backend specified here and the capacity and access modes here. Now obviously depending on the storage type, on the storage backend, some of the attributes in the specification will be different, because they're specific to the storage type. This is another example of a local storage, which is on the node itself, which has additional node affinity attribute. Now, you don't have to remember and know all these attributes at once, because you may not need all of them. And also, I will make separate videos covering some of the most used volumes and explain them individually with examples and demos. So there I'm going to explain in more detail which attributes should be used for these specific volumes and what they actually mean. In the official Kubernetes documentation, you can actually see the complete list of more than 25 storage backends that Kubernetes supports. Note here that persistent volumes are not namespaced, meaning they're accessible to the whole cluster, and unlike other components that we saw like pods and services, they're not in any namespace. They're just available to the whole cluster, to all the namespaces. Now it's important to differentiate here between two categories of the volumes, local and remote. Each volume type in these two categories has its own use case. Otherwise they won't exist, and we will see some of these use cases later in this video. However, the local volume types violate the second and third requirements of data persistence for databases that I mentioned at the beginning, which is one, not being tied to one specific node, but rather to each node equally, because you don't know where the new pod will start. And the second, surviving in cluster crash scenarios. Because of these reasons, for database persistence, you should almost always use remote storage. So who creates these persistent volumes and when? As I said, persistent volumes are resources like CPU or RAM, so they have to be already there in the cluster when the pod that depends on it or that uses it is created. So a side note here is that there are two main roles in Kubernetes. There's an administrator who sets up the cluster and maintains it, and also makes sure the cluster has enough resources. These are usually system administrators or DevOps engineers in a company. And the second role is Kubernetes user that deploys the applications in the cluster either directly or through CI pipeline. These are developer DevOps teams who create the applications and deploy them. So in this case, the Kubernetes administrator would be the one to configure the actual storage, meaning to make sure that the NFS server storage is there and configured, or maybe create and configure a cloud storage that will be available for the cluster. And second, create persistent volume components from these storage backends, based on the information from developer team of what types of storage their applications would need. And the developers then will know that storage is there and can be used by their applications. But for that, developers have to explicitly configure the application YAML file to use those persistent volume components. In other words, application has to claim that volume storage, and you do that using another component of Kubernetes called persistent volume claim. Persistent volume claims, also PVCs, are also created with YAML configuration. Here's an example claim. Again, don't worry about understanding each and every attribute that is defined here, but on the higher level, the way it works is that PVC claims a volume with certain storage size or capacity, which is defined in the persistent volume claim, and some additional characteristics, like access type. Should it be read-only or read-write, or the type, etc. And whatever persistent volume matches this criteria, or in other words, satisfies this claim, will be used for the application. But that's not all. You have to now use that claim in your pod's configuration, like this. So in the pod specification here, you have the volumes attribute that references the persistent volume claim with its name. So now the pod and all the containers inside the pod will have access to that persistent volume storage. So to go through those levels of abstraction step by step, pods access storage by using the claim as a volume, right? So they request the volume through claim. The claim then will go and try to find a volume, persistent volume in the cluster that satisfies the claim. And the volume will have a storage, the actual storage backend that it will create that storage resource from. And this way, the pod will now be able to use that actual storage backend. Note here that claims must exist in the same namespace as the pod using the claim, while, as I mentioned before, persistent volumes are not namespaced. So once the pod finds the matching persistent volume through the volume claim, through the persistent volume claim, the volume is then mounted into the pod like this here. This is a pod level. And then that volume can be mounted into the container inside the pod, which is this level right here. And if you have multiple containers here in the pod, you can decide to mount this volume in all the containers or just some of those. So now the container and the application inside the container can read and write to that storage. And when the pod dies and a new one gets created, it will have access to the same storage and see all the changes the previous pod or the previous containers made. Again, the attributes here like volumes and volume mounts, etc., and how they're used, I will show you more specifically and explain in a later demo video. Now, you may be wondering why so many abstractions for using volume, where admin role has to create persistent volume and user role creates a claim on that persistent volume, and that is then used in pod. Can I just use one component and configure everything there? Well, this actually has a benefit because as a user, meaning a developer who just wants to deploy their application in the cluster, you don't care about where the actual storage is. You know, you want your database to have persistence, and whether the data will live on a Gluster FS or AWS EBS or local storage doesn't matter for you, as long as the data is safely stored. Or if you need a directory storage for files, you don't care where the directory actually lives, as long as it has enough space and works properly. And you sure don't want to care about setting up these actual storages yourself. You just want 50 gigabyte storage for your Elastic or 10 gigabyte for your application, that's it. So you make a claim for storage using PVC and assume that cluster has storage resources already there. And this makes deploying the applications easier for developers because they don't have to take care of the stuff beyond deploying the applications. Now, there are two volume types that I think needs to be mentioned separately because they're a bit different from the rest, and these are config map and secret. Now, if you have watched my other video on Kubernetes components, then you are already familiar with both. Both of them are local volumes, but unlike the rest, these two aren't created via PV and PVC, but are rather own components and managed by Kubernetes itself. Consider a case where you need a configuration file for your Prometheus pod, or maybe a message broker service like Mosquito, or consider when you need a certificate file mounted inside your application. In both cases, you need a file available to your pod. So how this works is that you create config map or secret component, and you can mount that into your pod and into your container the same way as you would mount persistent volume claim. So instead you would have a config map or secret here. And I will show you a demo of this in a video where I cover local volume types. So to quickly summarize what we've covered so far, as you see at its core, a volume is just a directory, possibly with some data in it, which is accessible to the containers in a pod. How that directory is made available or what storage medium actually backs that, and the contents of that directory are defined by a specific volume type you use. So to use a volume, a pod specifies what volumes to provide for the pod in the specification volumes attribute. And inside the pod, then you can decide where to mount that storage into using volume mounts attribute inside the container section. And this is a path inside the container where application can access whatever storage we mounted into the container. And as I said, if you have multiple containers, you can decide which container should get access to that storage. Interesting note for you is that a pod can actually use multiple volumes of different types simultaneously. Let's say you have an Elasticsearch application or pod running in your cluster that needs a configuration file mounted through config map, needs a certificate, let's say client certificate, mounted as a secret, and it needs database storage, let's say, which is backed with AWS Elastic Block Storage. So in this case, you can configure all three inside your pod or deployment. So this is the pod specification that we saw before. And here on the volumes level, you will just list all the volumes that you want to mount into your pod. So let's say you have a persistent volume claim that in the background claims persistent volume from AWS block storage. And here you have the config map, and here you have a secret. And here in the volume mounts, you can list all those storage mounts using the names, right? So you have the persistent storage, then you have the config map and the secret, and each one of them is mounted to a certain path inside the container. Now we saw that to persist data in Kubernetes, admins need to configure storage for the cluster, create persistent volumes, and developers then can claim them using PVCs. But consider a cluster with hundreds of applications where things get deployed daily and storage is needed for these applications. So developers need to ask admins to create persistent volumes they need for applications before deploying them, and admins then may have to manually request storage from cloud or storage provider and create hundreds of persistent volumes for all the applications that need storage manually, and that can be tedious, time-consuming, and can get messy very quickly. So to make this process more efficient, there is a third component of Kubernetes persistence called storage class. Storage class basically creates or provisions persistent volumes dynamically whenever PVC claims it. And this way, creating or provisioning volumes in a cluster may be automated. Storage class also gets created using YAML configuration file. So this is an example file where we have the kind storage class. Storage class creates persistent volumes dynamically in the background. So remember, we defined storage backend in the persistent volume component. Now we have to define it in the storage class component. And we do that using the provisioner attribute, which is the main part of the storage class configuration because it tells Kubernetes which provisioner to be used for a specific storage platform or cloud provider to create the persistent volume component out of it. So each storage backend has its own provisioner that Kubernetes offers internally, which are prefixed with kubernetes.io, like this one here. And these are internal provisioners. And for others or other storage types, they are external provisioners that you have to then explicitly go and find and use that in your storage class. And in addition to provisioner attribute, we configure parameters of the storage we want to request for our persistent volume, like these ones here. So storage class is basically another abstraction level that abstracts the underlying storage provider as well as parameters for that storage, or characteristics for the storage, like what disk type or etc. So how does it work, or how do we use storage class in the pod configuration? Same as persistent volume, it is requested or claimed by PVC. So in the PVC configuration, here we add additional attribute that is called storage class name that references the storage class to be used to create a persistent volume that satisfies the claims of this PVC. So now when a pod claims storage through PVC, the PVC will request that storage from storage class, which then will provision or create persistent volume that meets the needs of that claim using provisioner from the actual storage backend. Now, this should help you understand the concepts of how data is persisted in Kubernetes as a high-level overview. In this video, we're going to talk about what stateful set is in Kubernetes and what purpose it has. So what is stateful set? It's a Kubernetes component that is used specifically for stateful applications. So in order to understand that, first you need to understand what a stateful application is. Examples of stateful applications are all databases like MySQL, Elasticsearch, MongoDB, etc., or any application that stores data to keep track of its state. In other words, these are applications that track state by saving that information in some storage. Stateless applications, on the other hand, do not keep records of previous interaction, and each request or interaction is handled as a completely new, isolated interaction, based entirely on the information that comes with it. And sometimes stateless applications connect to the stateful application to forward those requests. So imagine a simple setup of a Node.js application that is connected to MongoDB database. When a request comes in to the Node.js application, it doesn't depend on any previous data to handle this incoming request. It can handle it based on the payload in the request itself. Now, a typical such request will additionally need to update some data in the database or query the data. That's where MongoDB comes in. So when Node.js forwards that request to MongoDB, MongoDB will update the data based on its previous state or query the data from its storage. So for each request, it needs to handle data and obviously always depends on the most up-to-date data or state to be available. While Node.js is just a pass-through for data updates or queries, and it just processes code. Now, because of this difference between stateful and stateless applications, they're both deployed in different ways using different components in Kubernetes. Stateless applications are deployed using deployment component, where deployment is an abstraction of pods and allows you to replicate that application, meaning run 2, 5, 10 identical pods of the same stateless application in the cluster. So while stateless applications are deployed using deployment, stateful applications in Kubernetes are deployed using stateful set components. And just like deployment, stateful set makes it possible to replicate the stateful app pods or to run multiple replicas of it. In other words, they both manage pods that are based on an identical container specification. And you can also configure storage with both of them equally in the same way. So if both manage the replication of pods and also configuration of data persistence in the same way, the question is what a lot of people ask and are also often confused about: what is the difference between those two components? Why we use different ones for each type of application? So in the next section, we're going to talk about the differences. Now, replicating stateful application is more difficult and has a couple of requirements that stateless applications do not have. So let's look at this first with the example of a MySQL database. Let's say you have one MySQL database pod that handles requests from a Java application, which is deployed using a deployment component. And let's say you scale the Java application to 3 pods so they can handle more client requests. In parallel, you want to scale MySQL app so it can handle more Java requests as well. Scaling your Java application here is pretty straightforward. Java applications replica pods will be identical and interchangeable. So you can scale it using a deployment pretty easily. Deployment will create the pods in any order, in any random order. They will get random hashes at the end of the pod name. They will get one service that load balances to any one of the replica pods for any request. And also when you delete them, they get deleted in a random order or at the same time, right? Or when you scale them down from 3 to 2 replicas, for example, one random replica pod gets chosen to be deleted. So no complications there. On the other hand, MySQL pod replicas cannot be created and deleted at the same time in any order, and they can't be randomly addressed. And the reason for that is because the replica pods are not identical. In fact, they each have their own additional identity on top of the common blueprint of the pod that they get created from. And giving each pod its own required individual identity is actually what stateful set does, different from deployment. It maintains a sticky identity for each of its pods. And as I said, these pods are created from the same specification, but they're not interchangeable. Each has a persistent identifier that it maintains across any rescheduling. So meaning when pod dies and it gets replaced by a new pod, it keeps that identity. So the question you may be asking now is, why do these pods need their own identities? Why they can't be interchangeable just like with deployment? So why is that? And this is a concept that you need to understand about scaling database applications in general. When you start with a single MySQL pod, it will be used for both reading and writing data. But when you add a second one, it cannot act the same way, because if you allow 2 independent instances of MySQL to change the same data, you will end up with data inconsistency. So instead, there is a mechanism that decides that only one pod is allowed to write or change the data which is shared, reading at the same time by multiple pods, MySQL instances from the same data is completely fine. And the pod that is allowed to update the data is called the master. The others are called slaves. So this is the first thing that differentiates these pods from each other. So not all pods are same, identical, but there is a master pod and there are the slave pods, right? And there's also difference between those slave pods in terms of storage, which is the next point. So the thing is that these pods do not have access to the same physical storage. Even though they use the same data, they're not using the same physical storage of the data. They each have their own replicas of the storage that each one of them can access for itself. And this means that each pod replica at any time must have the same data as the other ones. And in order to achieve that, they have to continuously synchronize their data. And since master is the only one allowed to change data, and the slaves need to take care of their own data storage, obviously the slaves must know about each such change so they can update their own data storage. to be up to date for the next query requests. And there's a mechanism in such clustered database setup that allows for continuous data synchronization. Master changes data, and all slaves update their own data storage to keep in sync and to make sure that each pod has the same state. Now let's say you have one master and two slave pods of MySQL. Now what happens when a new pod replica joins the existing setup? Because now that new pod also needs to create its own storage and then take care of synchronizing it. What happens is that it first clones the data from the previous pod, not just any pod in the setup, but always from the previous pod. And once it has the up-to-date data cloned, it starts continuous synchronization as well to listen for any updates by master pod. And this also means, and I want to point this out since it's a pretty interesting point, it means that you can actually have a temporary storage for a stateful application and not persist the data at all, since the data gets replicated between the pods. So theoretically, it is possible to just rely on data replication between the pods. But this will also mean that the whole data will be lost when all the pods die. So for example, if stateful set gets deleted or the cluster crashes or all the nodes where these pod replicas are running crash and every pod dies at the same time, the data will be gone. And therefore, it's still a best practice to use data persistence for stateful applications if losing the data will be unacceptable, which is the case in most database applications. And with persistent storage, data will survive even if all the pods of the stateful set die. Or even if you delete the complete stateful set component and all the pods get wiped out as well, the persistent storage and the data will still remain. Because persistent volume lifecycle isn't connected or isn't tied to a lifecycle of other components like deployment or stateful set. And the way to do this is configuring persistent volumes for your stateful set. And since each pod has its own data storage, meaning it's the own persistent volume that is then backed up by its own physical storage, which includes the synchronized data or the replicated database data, but also the state of the pod. So each pod has its own state, which has information about whether it's a master pod or a slave or other individual characteristics. And all of this gets stored in the pod's own storage. And that means when a pod dies and gets replaced, the persistent pod identifiers make sure that the storage volume gets reattached to the replacement pod. As I said, because that storage has the state of the pod in addition to that replicated data. I mean, you can clone the data again, that will be no problem, but it shouldn't lose its state or identity state, so to say. And for this reattachment to work, it's important to use a remote storage, because if the pod gets rescheduled from one node to another node, the previous storage must be available on the other node as well. And you cannot do that using local volume storage because they are usually tied to a specific node. And the last difference between deployment and stateful set is something that I mentioned before, is the pod identifier, meaning that every pod has its own identifier. So unlike deployment, where pods get random hashes at the end, stateful set pods get fixed ordered names, which is made up of the stateful set name and an ordinal. It starts from 0, and each additional pod will get the next numeral. So if you create a stateful set called MySQL with 3 replicas, you'll have pods with names MySQL 0, 1, and 2. The first one is the master, and then come the slaves in the order of startup. An important note here is that the stateful set will not create the next pod in the replica if the previous one isn't already up and running. If first pod creation, for example, failed, or if it was pending, the next one won't get created at all. It will just wait. And the same order is held in deletion, but in reversed order. So for example, if you deleted the stateful set, or if you scaled it down to 1, for example, from 3, the deletion will start from the last pod. So MySQL 2 will get deleted first. It will wait until that pod is successfully deleted, and then it will delete MySQL 1, and then it will delete MySQL 0. And again, all these mechanisms are in place in order to protect the data and the state that the stateful application depends on. In addition to these fixed predictable names, each pod in a stateful set gets its own DNS endpoint from a service. So there's a service name for the stateful application, just like for deployment, for example, that will address any replica pod. And plus, in addition to that, there is individual DNS name for each pod, which deployment pods do not have. The individual DNS names are made up of pod name and the manage or the governing service name, which is basically a service name that you define inside the stateful set. So these two characteristics, meaning having a predictable or fixed name as well as its fixed individual DNS name, means that when pod restarts, the IP address will change, but the name and endpoint will stay the same. That's why I said pods get sticky identities. So it gets stuck to it even between the restarts. And the sticky identity makes sure that each replica pod can retain its state and its role even when it dies and gets recreated. And finally, I want to mention an important point here. As you see, replicating stateful apps like databases with its persistent storage requires a complex mechanism. And Kubernetes helps you and supports you to set this whole thing up, but you still need to do a lot by yourself, where Kubernetes doesn't actually help you or doesn't provide you out-of-the-box solutions. For example, you need to configure the cloning and data synchronization inside the stateful set and also make the remote storage available, as well as take care of managing and backing it up. All of this you have to do yourself. And the reason is that stateful applications are not a perfect candidate for containerized environments. In fact, Docker, Kubernetes, and generally containerization is perfectly fitting for stateless applications that do not have any state and data dependency and only process code, so scaling and replicating them in containers is super easy. In this video, I will give you a complete overview of Kubernetes services. First, I'll explain shortly what service component is in Kubernetes and when we need it. And then we'll go through the different service types: cluster IP service, headless service, node port, and load balancer services. I will explain the differences between them and when to use which one. So by the end of the video, you'll have a great understanding of Kubernetes services and will be able to use them in practice. So let's get started. So what is a service in Kubernetes and why do we need it? In a Kubernetes cluster, each pod gets its own internal IP address, but the pods in Kubernetes are ephemeral, meaning that they come and go very frequently, and when the pod restarts or when old one dies and the new one gets started in its place, it gets a new IP address. So it doesn't make sense to use pod IP addresses directly because then you would have to adjust that every time the pod gets recreated. With a service, however, you have a solution of a stable or static IP address that stays even when the pod dies. So basically in front of each pod, we set a service, which represents a persistent, stable IP address, access that pod. A service also provides load balancing because when you have pod replicas, for example, 3 replicas of your microservice application or 3 replicas of MySQL application, the service will basically get each request targeted to that MySQL or your microservice application and then forward it to one of those pods. So clients can call a single stable IP address instead of calling each pod individually. So services are a good abstraction for loose coupling for communication within the cluster, so within the cluster components or pods inside the cluster, but also from external services, like if you have browser requests coming to the cluster, or if you're talking to an external database, for example. There are several types of services in Kubernetes. The first and the most common one that you probably will use most of the time is the cluster IP type. This is a default type of a service, meaning when you create a service and not specify a type, it will automatically take cluster IP as a type. So let's see how cluster IP works and where it's used in Kubernetes setup. Imagine we have a microservice application deployed in the cluster. So we have a pod with microservice container running inside that pod. And beside that microservice container, we have a sidecar container that collects the logs of the microservice and then sends that to some destination database. So these 2 containers are running in the pod. And let's say your microservice container is running at pod 3000 and your logging container, let's say, is running on port 9000. This means that those 2 ports will be now open and accessible inside the pod. And pod will also get an IP address from a range that is assigned to a node. So the way it works is that if you have, for example, 3 worker nodes in your Kubernetes cluster, each worker node will get a range of IP addresses, which are internal in the cluster. So for example, the pod 1 will get IP addresses from a range of 10.2.1 onwards. The second worker node will get this IP range, and the third worker node will get this one. So let's say this pod starts on node 2, so it gets an IP address that looks like this. If you want to see the IP addresses of your pods in the cluster, you can actually check them using kubectl get pod output wide command, where you will get some extra information about the pods, including its IP address. And here you will see the IP address that it got assigned. And as I mentioned, these are from the IP address range that each worker node in the cluster will get. So this is from the first worker node, and these are from the second worker node. So now we can access those containers inside the pod at this IP address at these ports. If we set the replica count to 2, we're going to have another pod which is identical to the first one, which will open the same ports and it will get a different IP address. Let's say if it starts on worker node 1, it will get an IP address that looks something like this. Now, let's say this microservice is accessible through a browser. So we have ingress configured and the request coming in from the browser to the microservice will be handled by ingress. How does this incoming request get forwarded from ingress all the way to the pod? And that happens through a service, a cluster IP or so-called internal service. A service in Kubernetes is a component just like a pod, but it's not a process. It's just an abstraction layer that basically represents an IP address. So service will get an IP address that it is accessible at. And service will also be accessible at a certain port. Let's say we define that port to be 3200. So ingress will talk to the service or hand over the request to the service at this IP address at this port. So this is how service is accessible within the cluster. So the way it works is that we define ingress rules that forward the request based on the request address to certain services. And we define the service by its name. And the DNS resolution then maps that service name to an IP address that the service actually got assigned. So this is how ingress knows how to talk to the service. So once the request gets handed over to the service at this address, then service will know to forward that request to one of those pods that are registered as the service endpoints. Now here are two questions. How does service know which pods it is managing or which pods to forward the request to? And the second one is, how does service know which port to forward that request to on that specific pod? The first one is defined by selectors. A service identifies its member pods or its endpoint pods using a selector attribute. So in the service specification, in the YAML file from which we create the service, we specify the selector attribute that has a key value pairs defined as a list. Now these key value pairs are basically labels that pods should have to match that selector. So in the pod configuration file, we assign the pod certain labels in the metadata section. And these labels can be arbitrary names. So we can say my app, for example, and give it some other labels. This is basically something that we define ourselves. We can give it any name that we want. These are just key value pairs that identify a set of pods. And in the service YAML file, then we define a selector to match any pod that has all of these labels. This means if we have a deployment component that creates 3 replicas of pods with a label called app my app and type microservice, for example, and in the service selector attribute, we define those 2 labels, then service will match all of those 3 pod replicas. And it will register all 3 pods as its endpoints. And as I said, it should match all the selectors, not just one. So this is how service will know which pods belong to it, meaning where to forward that request to. The second question was, if a pod has multiple ports open where 2 different applications are listening inside the pod, how does service know which port to forward the request to? And this is defined in the target port attribute. So this target port attribute, so let's say target port in our example is 3000. What this means is that when we create the service, it will find all the pods that match this selector. So these pods will become endpoints of the service. And when the service gets a request, it will pick one of those pod replicas randomly because it's a load balancer, and it will send the request it received to that specific pod on a port defined by target port attribute. In this case, 3000. Also note that when you create a service, Kubernetes creates an endpoints object that has the same name as the service itself, and Kubernetes will use this endpoints object to keep track of which pods are members of the service. Or as I said, which pods are the endpoints of the service. And since this is dynamic, because whenever you create a new pod replica or a pod dice, the endpoints get updated, so this object will basically track that. And note here that the service port itself is arbitrary, so you can define it yourself, whereas the target port is not arbitrary. It has to match the port where container, the application container inside the pod, is listening at. Now let's say our microservice application got its request from the browser through ingress and internal cluster IP service, and now it needs to communicate with the database to handle that request, for example. And in our example, let's assume that the microservice application uses MongoDB database. So we have 2 replicas of MongoDB in the cluster, which also have their own service endpoint. So MongoDB service is also of cluster IP, and it has its own IP address. So now the microservice application inside the pod can talk to the MongoDB database also using the service endpoint. So the request will come from one of the pods that gets the request from the service to the MongoDB service at this IP address and the port that service has open. And then service will again select one of those pod replicas and forward that request to the selected pod at the port, the target port defined here. And this is the port where MongoDB application inside the pod is listening at. Now let's assume that inside that MongoDB pod, there is another container running that selects the monitoring metrics for Prometheus, for example. And that will be a MongoDB exporter. And that container, let's say, is running at port 9216. And this is where the application is accessible at. And in the cluster, we have a Prometheus application that scrapes the metrics endpoint from this MongoDB exporter container from this endpoint. Now that means that service has to handle two different endpoint requests, which also means that service has two of its own ports open for handling these two different requests. One from the clients that want to talk to the MongoDB database, and one from the clients like Prometheus that want to talk to the MongoDB exporter application. And this is an example of a multi-port service. And note here that when you have multiple ports defined in a service, you have to name those ports. If it's just one port, then you can leave it, so to say, anonymous. You don't have to use the name attribute, it's optional. But if you have multiple ports defined, then you have to name each one of those. So these were examples of cluster IP service type. Now let's see another service type, which is called headless service. So let's see what headless service type is. As we saw, each request to the service is forwarded to one of the pod replicas that are registered as service endpoints. But imagine if a client wants to communicate with one of the pods directly and selectively. Or what if the endpoint pods need to communicate with each other directly without going through the service? Obviously, in this case, it would make sense to talk to the service endpoint, which will randomly select one of the pods, because we want the communication with specific pods. Now, what would be such a use case? A use case where this is necessary is when we're deploying stateful applications in Kubernetes. Stateful applications like databases, MySQL, MongoDB, Elasticsearch, and so on. In such applications, the pod replicas aren't identical, but rather each one has its individual state and characteristic. For example, if we're deploying a MySQL application, you would have a master instance of MySQL and worker instances of MySQL application. And master is the only pod allowed to write to the database, and the worker pods must connect to the master to synchronize their data after master pod has made changes to the database. So they get the up-to-date data as well. And when new worker pod starts, it must connect directly to the most recent worker node to clone the data from and also get up to date with the data state. So that's the most common use case where you need direct communication with individual pods. For such case, for a client to connect to all pods individually, it needs to figure out the IP address of each individual pod. One option to achieve this would be to make an API call to Kubernetes API server, and it will return the list of pods and their IP addresses. But this will make your application too tied to the Kubernetes specific API. And also this will be inefficient because you will have to get the whole list of pods and their IP addresses every time you want to connect to one of the pods. But as an alternative solution, Kubernetes allows clients to discover pod IP addresses through DNS lookups. And usually the way it works is that when a client performs a DNS lookup for a service, the DNS server returns a single IP address which belongs to the service. And this will be the service's cluster IP address, which we saw previously. However, if you tell Kubernetes that you don't need a cluster IP address of the service, by setting the cluster IP field to none when creating a service, then the DNS server will return the pod IP addresses instead of the service's IP address. And now the client can do a simple DNS lookup to get the IP address of the pods that are members of that service. And then client can use that IP address to connect to the specific pod it wants to talk to or all of the pods. So the way we define a headless service in a service configuration file is basically setting the cluster IP to none. So when we create this service from this configuration file, Kubernetes will not assign the service a cluster IP address. And we can see that in the output when I list my services. So I have a cluster IP service that I created for the microservice and a headless service. And note here that when we deploy stateful applications in the cluster, like MongoDB, for example, we have the normal service, the cluster IP service, that basically handles the communication to MongoDB and maybe other container inside the pod. And in addition to that service, we have a headless service. So we always have these two services alongside each other. So this can do the usual load balancing stuff for this kind of use case, and for use cases where client needs to communicate with one of those pods directly, like a master node directly to perform the write commands, or the pods to talk to each other for data synchronization, the headless service will be used for that. When we define a service configuration, we can specify a type of the service, and the type attribute can have 3 different values. It could be cluster IP, which is a default. That's why we don't have to specify that. We have a node port and load balancer. So type node port basically creates a service that is accessible on a static port on each worker node in the cluster. Now to compare that to our previous example, the cluster IP service is only accessible within the cluster itself. So no external traffic can directly address the cluster IP service. The node port service, however, makes the external traffic accessible on static or fixed port on each worker node. So in this case, instead of ingress, the browser request will come directly to the worker node at the port that the service specification defines. And the port that node port service type exposes is defined in the node port attribute. And here note that the node port value has a predefined range between 30,000 and 32,767. So you can have one of the values from that range as a node port value. Anything outside that range won't be accepted. So this means that the node port service is accessible for the external traffic, like browser requests, for example, at IP address of the worker node and the node port defined here. However, just like in cluster IP, we have a port of the service. So when we create the node port service, a cluster IP service to which the node port service will route is automatically created. And here, as you see, if I list the services, the node port will have a cluster IP address, and for each IP address, it will also have the ports open where the service is accessible at. And also note that the service spans all the worker nodes. So if you have 3 pod replicas on 3 different nodes, basically the service will be able to handle that request coming on any of the worker nodes and then forward it to one of those pod replicas. Now, that type of service exposure is not very efficient and also not secure because you're basically opening the ports to directly talk to the services on each worker node, so the external clients basically have access to the worker nodes directly. So if we gave all the services this node port service type, then we would have a bunch of ports open on the worker nodes clients from outside can directly talk to. So it's not very efficient and secure way to handle that. And as a better alternative, there is a load balancer service type. And the way it works with load balancer service type is that the service becomes accessible externally through a cloud provider's load balancer functionality. So each cloud provider has its own native load balancer implementation, and that is created and used whenever we create a load balancer service type. Google Cloud Platform, AWS, Azure, Linode, OpenStack, and so on, all of them offer this functionality. So whenever we create a load balancer service, node port and cluster IP services are created automatically by Kubernetes, to which the external load balancer of the cloud platform will route the traffic to. And this is an example of how we define load balancer service configuration. So instead of node port type, we have a load balancer, and the same way we have the port of the service, which belongs to the cluster IP, and we have the node port, which is the port that opens on the worker node, but it's not directly accessible externally, but only through the load balancer itself. So the entry point becomes the load balancer first, and it can then direct the traffic to node port on the worker node and the cluster IP, the internal service. So that's how the flow would work with the load balancer service. So in other words, the load balancer service type is an extension of the node port type, which itself is an extension of the cluster IP type. And again, if I create a load balancer service type and list all the services, you can see the differences in the display as well. Where for each service type, you see the IP addresses, you see the type, and you see the ports that the service has opened. And I should mention here that in a real Kubernetes setup example, you would probably not use node port for external connection. You would maybe use it to test some service very quickly, but not for production use cases. So for example, if you have an application that is accessible through browser, you will either configure ingress for each such request. So you would have internal services, the cluster IP services that ingress will route to, or you would have a load balancer that uses the cloud platform's native load balancer implementation. Congratulations, you made it till the end. I hope you learned a lot and got some valuable knowledge from this course. If you want to learn about modern DevOps tools, be sure to check out my tutorials on that topic and subscribe to my channel for more content. Also, if you want to stay connected, you can follow me on social media or join the private Facebook group. I would love to see you there. So thank you for watching and see you in the next video.
Okay guys, absolutely fantastic. I love Nana. She's such a great teacher. And finally, didn't think I'd do it this video, but have finished that course, so that's amazing. What am I going to do now? Am I going to go back to React, or will I go back to and do a bit more Kubernetes and try and get something actually working? To be honest, I'm missing React a bit, and I feel like I have a good base of Kubernetes for moving forward. You know, those little errors that I was having, they just have to be worked out in real time when you're actually doing it. But maybe I will come back and do another Kubernetes tutorial just to fly through something that actually is going to work. But I miss Max as well, so look, we'll figure all that out. No point in worrying about it now. You know, we'll just let it unfold. So thanks so much for joining me, guys. Really appreciate it, and have a super duper day. Thanks so much, guys. Peace.